Warahmatullahi wabarakatuh. Hello everyone, this is Mr. Ahmed Mansouri, and this is a video that's gonna explain to you chapter 16 in your book, which is the third chapter of Unit 4, speaking about energies and what comes afterwards. The chapter itself is not that much complicated. In reality, it's to do with simple calculations, and they all go back to the law of conservation of energy, so it's just a little bit of basis that you need to make sure you understand very well. Calculations wise and questions wise, when it comes to that, they're not that complicated at all. In fact, it's one of the easiest chapters in the book, if you ask me. It discusses an idea that in physics there is a way for you to measure the amount of mechanical energy done, okay? And this way of measuring mechanical energy is defined for you to be something that we're gonna identify as work. Okay, and work is very simple. Work basically just takes in consideration objects moving from one place to another due to a certain force. Meaning, if you have a box, all right, and the box is placed in a certain position on the ground, okay, in order for you to move it a certain distance from here to wherever you want to take it, let's say you just want to push it a little bit to the side, you need something to use some sort of energy to move this box, because it wouldn't go on its own. And that's something that we understand. Some sort of force needs to be applied on the box to take it from there to the new position it's supposed to be in, which is right here. All right. Now, the way this chapter explains this idea about pushing objects from one place to another is very simple. It just identifies it as something called work, which is a certain force. Let's assume that a man just came from this side and suddenly held the box and started pushing it. Okay, a certain force pushing an object a certain distance. Okay, work is very simple. In a not complicated way, it just tells you that if you're trying to make an object move from a position to another, I'm only gonna care about two things and you should know them. How much force did you push this box with, and how much distance did it move? Making those two things factors in calculating the work. Meaning, if this box didn't move from here to here, no, it had a longer distance to go. And forget about the imaginary example I gave you that the box lands right here. Imagine if the box had to be pushed further away. This causes the total work that this poor man has to do to be bigger. Now imagine if another scenario where the box, instead of it being this small little box that we have right there, it's a bigger box and it's heavier. And it's gonna travel the same distance as we can see right here to this position. So imagine that the box that we have right here is the bigger box, and we want to move it from this position to that position. Now, this guy, whoever we're gonna hire for the second job, is gonna have to apply far more work or a bigger force to push the box from here all the way to the other end on the other side. All of these factors combined make us understand that in general, work done is just the amount of energy used to move objects by knowing two main factors, which are how much force was used in moving the object, multiply how much distance did I move the object. Okay, an increase in either of them, an increase in the amount of force, okay, or an increase in the distance that we move it is gonna cause an increase in work instantly. All right, making them both directly proportional to it. Okay, now according to everything that we discussed, we said that the work done is a factor of two things that we identified to be the force applied on the object and how much distance it moves. Okay, and now we need a little bit of thinking to understand like two things that are obvious, but if they're not that obvious, you need to think about them slowly. Any two numbers multiplied by each other, if we make, and this is going to be very important even to explain the next points that we're going to talk about, if we make either of the two numbers a zero, that means the total amount that's going to come on the other side is going to be a zero. All right, now if you don't understand that, I want you to take a look at what I'm going to do right now. Imagine scenarios, because they always make things easier to comprehend. Imagine the man that we talked about a few minutes ago, okay, is trying to push the box, okay, and he's trying to move it a certain distance, but the problem is the box that we have in question happens to be very heavy. All right, now this man right here applies a big force, okay, on the box, but the reality of it, it simply doesn't move, making the distance it moved equal zero, because the box being too heavy, no matter how much force he applies on it, it doesn't end up moving at all. If you go back to the main formula of work, you'll find that it's a multiplication of the force of the man multiplied by how much distance did he move the box, except for we know that the distance in this case is 0 because the box happened to be too heavy for him to move. Now, work in this case, you should ask yourself, does work exist? Does it not exist? Because the man did actually try to push the box, but unfortunately it didn't move. This makes us understand one thing that's very, very, very simple. It doesn't matter how much force you apply on an object. If it doesn't move, your work is always 0. Okay, and let's take it in numbers for you to understand. Imagine that the man was applying 500 newtons trying to push the box forward. Again, it's too heavy, it doesn't move, the distance is 0. You go on the formula, you put instead of the force 500 newtons, you multiply it by the distance, which is 0, and we know that any number multiplied by 0, is going to give us 0. So therefore, work has to have both of those conditions in order for it to exist. Somebody needs to apply, or an object needs to apply a certain force, and it needs to move the object in which the force is being applied on. Either of those conditions doesn't exist, automatically your work automatically happens to be 0. All right? Sometimes you apply a force on an object, such as this one right here. The man is trying to push the box, and yet it does not move. And this is a very common scenario, but what you should understand is if this scenario occurs, your work is always 0. For a very simple explanation, that even though you have force, you don't have distance. Distance is 0. And if you take both of them, your force, which takes a certain value, no matter what it is, and multiply it by 0, like we see right here, the result will always be 0. All right. Out of all of that, we're going to go over a quick summary to discuss everything that we spoke about in this page right here. Work in definition, it says that it's when an object is moved over a distance by a force. So again, I'm repeating the exact same points because I want you to understand the idea of it. The object has to move, and it needs to move the distance, obviously, that we're discussing, by a force. So if you have distance moved and you have force applied, that automatically you have work. All right. It says on this third line right here, it says if an applied force doesn't result in any movement, then your work is automatically 0. Again, the exact same point that we're discussing. And finally, it says that work is measured in joules. All right, and this is something that you should know and you shouldn't forget about, that the unit that we use to measure work is joules. All right. Now, what we've been discussing from the beginning of this chapter is work, but we need to find a connection to it and with everything that we discussed before, which is energies and how do they operate. The problem with work is very simple. According to what we said, work is something that happens when a force moves a certain object a certain distance. In order for you to move this object, you need to apply a force on it. Okay, and it will automatically start moving into a distance. Now, the problem with all of this is not the distance itself, as you can always measure the distance moved by an object. In the boxes examples that we took up there, you can always take a look, all right, and you can figure out how much this distance is from here, for example, all the way to here. And it can be 3 meters, 2 meters, depending on the measurement that you take. That's not the idea that's difficult right here. Because always distance can be measured and it's easy to calculate stuff with it because it's a measurement. Now the problem is force. We don't have a certain way where we can measure forces. No, in order for us to determine forces, we always use other calculations. Okay, making work as an idea of energy of movement seem a bit complicated, since every time you need to do it, you need to figure out the force, and for you to figure out the force, you need to include other calculations, and it gets longer, while when you look at distance, you just need to find any measurement tool, like a ruler, a meter, or whatever, and take the distance. This causes an issue, and the solution to it is that we have other types of energies of movement, which we already discussed lightly in the previous lessons. And the energies of movement which we discussed lightly in the previous lessons happen to be the kinetic energy and the gravitational, let's just write it in short to not waste time. It happens to be the gravitational potential energy. All right. We discussed that both of these have something to do with movement, and if you remember with me, I told you that in the future lessons we're going to learn how to calculate them and all of that. For now, I'm not going to go deep into either of them, this one or this one, but they're going to be the next thing we're going to focus about, mainly because work, if you don't know the force moving the object, becomes very, very difficult to deal with, And in some scenarios, you have to divide the problem into simpler problems such as kinetic energy and gravitational potential energy. Now, even though we're going to have to discuss those two ideas later in the future, the only reason I mentioned them is because I want you to understand this is an energy. This is also a gravitational potential energy. All right, meaning since work can be defined as those two, work also can be dealt with the same way we deal with energies. What does that mean to us? It means to us, just like every other energy, we had to measure it with joules. All right. So work also has to be measured with joules. Same as this one, same as this one, same as this one. And another thing is if you can figure out the total work done, and we'll see that in future problems, inshallah. If you can figure out the total work done, it will be always equal to the amount of energy used. Okay. And why am I saying this? We're going to take one last look at the box example at the very top right here. Okay. So the amount of work this man does on the box is the exact same amount of the kinetic energy that's going to move the box. All right, I hope that's not complicated, but the amount of work that's done by the weight here is the exact same amount of kinetic energy the ball is going to move with, meaning that work and the energies in general are equal. The only issue that you might face is that sometimes it's not one energy, it's multiple energies, and we're going to deal with that with problems, inshallah. It's nothing that's complicated. Now, we can focus about the issues that come with mixing up work and energies when the time is right. But again, it's nothing that's very, very serious. Right now, we're going to discuss some simple problems to do with calculating work, all right, or measuring work in certain scenarios. Those are past paper questions, but in reality, this topic is not complicated. Therefore, they always use them as startup questions. Like a question can have complicated parts. You might find the complicated part to be C or D or like at the very bottom, but the beginning of it is always very simple. Look at this question, for example. It says a man uses a wheelbarrow to carry some logs along a flat path as shown. You can see it. It's just somebody using a force because he's carrying them, and obviously that the cart is moving a certain distance. It tells you that he pushes, all right, with a horizontal force of 140 newtons. This is the force that we're looking for, all right? And the entire thing moves 39 meters, and that's the distance in this case. Very simple. It tells you to state the relationship between work, force, distance moved, and we already understand that work equals the force multiplied by the distance. Nothing complicated with that as well. You can go forward, and it says calculate the work done by the moving wheelbarrow, and all you need to do is multiply the force, which is 140 newtons, multiplied by the distance moved, which is 39 meters. Okay, and it's going to give you the work done if you do the calculation real quick, which happens to be 5,460, and the unit for work, as we agreed, is joules, just like every other energy that we discussed. Okay, finally, it says how much energy, state how much energy is transferred to the wheelbarrow. All right, now this is the point that I could give you the straight away answer to it, and it's very simple, but I want to explain it again to make sure that you guys understand it properly. Okay, again, this is the man. I'm gonna highlight him in a different color. Okay, and what the man is doing is he is applying work on the wheelbarrow. All right, the wheelbarrow is an object that doesn't have energy of movement at all. It only moves because this man is pushing it. Now, this man is pushing it with a certain work that we calculated it to be 5,460 joules, which means the wheelbarrow gets affected by 5,460 joules of energy. This is a very important point which you need to understand properly, even though it's not complicated. You need to understand that this cart on its own, or the wheelbarrow on its own, does not have energy, but because there is a man pushing it, suddenly it does have energy, which is 5,460 joules. This energy is not in the wheelbarrow itself, no, it's being applied on it. Okay, and because you're applying energy on it, it starts to move. And in this case, we can identify it to be kinetic energy, which is the energy of movement, and it makes it to roll forward. All right. So the answer to that, since the man is the one doing the work and he's doing 5,460 joules, the work, state how much energy is transferred to the wheelbarrow, the energy transfer to the wheelbarrow is the same, which is the man is applying as 5,460 joules, because there is no other thing pushing the wheelbarrow other than the man, and the man is using this amount of energy to push it, and all of it is going to the wheelbarrow, which is being pushed. So always understand with me a very, very, very simple rule here that I'm gonna write at the bottom here. The work done by an object, okay, is always equal to the energy transferred. So keep that in mind. Don't forget about it, even if you face it in future questions. This is the explanation behind it. But if you're just looking for the final answer quickly, just understand that the work done is always equal to the energy of transfer. Meaning if you calculated the energy transferred and it asks you for the work, understand they're equal. Even though in this question it gave it to us in the other way around, we already calculated the work done, and then it asked us what's the energy. All right, you just need to understand that those two are equal. Both of them are measured in joules. Both of them in certain scenarios have to equal each other. All right, moving on to the next question. We have that supermarkets use this device shape we have right here, which is the one that basically when you're going to pay, the roller thing that rolls on before you can beep the items. It just moves. It's telling you that it moved this carton of milk the distance of 0.49 meters, and it uses the force of 1.7 newtons to move it along. It's again a very, very, very simple problem. It asks you to write the equation of work one more time, and the equation says that work equals distance multiplied by force. Okay, and then you need to move on to the second point, which is calculate the work done by the moving carton right there. This is the milk carton it's talking about, and it's telling you that it moved the distance of 0.46 and the force moving it is 1.7. So all you need to say is work is 1.7 multiplied by 0.46, which is the force multiplied by the distance, and it's nothing difficult at all to deal with, and it's gonna give you the result of 0.782 joules. All right, this question is worth only 2 marks because it already mentioned the unit for you here as joules. If you take a look at the question up here, never mind. I thought it's gonna be 3 marks because of it. Apparently it's just easy. Okay, state how much energy is transferred to the carton. Again, same idea. What's moving the carton is this thing, the belt basically that's connected right here is what's responsible for moving the carton. The belt is applying work because it's moving an object a certain distance using a force, but I want you to take it from the perspective of the milk carton itself. The milk carton is just chilling, but there is something pushing it. So it feels like kind of there is an energy being applied on it that makes it move. Now, what's the energy being applied on it? It's the same as the work done by the belt, since the belt is the only thing moving it. We calculated the work done by the belt to be 0.782. So the energy transferred to the carton is also going to be 0.782, according to the exact same rule that we agreed on, that the work done is always the same as the energy transferred. I hope this is very clear. I repeated the exact same question twice only for you guys to understand that this is something that is very fundamental when it comes to understanding work. It's just a type of mechanical energy. I want you to think about it about the same thing. If you take anything from the table that you have in front of you right now, look at it, this object, whatever it is, a pencil case, a notebook, the book that you have, this object that you have in front of you does not have any sort of energy. But if you hold it with your hand and you pick it upwards a certain distance, that's you applying a certain force on the object, making it move up. So from the object's perspective, it's just feeling like there is an energy being transferred to it that makes it go from the ground or from the table all the way to a distance that's above a little bit. All right, so it's just a question that makes you, first of all, understand it from your perspective, and then secondly, from the object's perspective. Here it says a photographer shows a machine at a coal mine. All right, nothing crazy. The machine lifts a load weighing 400 Newton, and the distance it moves it is 190 meters. Say the relationship between work distance moved. I'm not going to write it. We wrote it too many times. Calculate the work done on the load. It already mentioned that the unit is in joules, so you just need to literally just multiply. Work equals force multiplied by distance Okay, and you just need to multiply both of these two together, which if you put them in the calculator, they would end up giving you the number of, I'm gonna write it here because I don't have the space to write it right there, which is 76 million joules. And if in the question it asked you to write it in another unit, which is megajoules, I'm just saying in case that was the question, you would need to understand that the word mega means a million, so you need to take all of these zeros away, and it would be 76 megajoules. Or because in certain questions like this one, it doesn't care about the unit that much, you can write it with joules normally, making the step that we did at the very beginning correct. And you just need to write it as 76 million joules or 76 megajoules. Both of them mean the same thing. Now, finally, as a summary, we just need to agree on a few things, which are the important things we're going to move on with to the next lesson. The formula of work stating that the work done, okay, is a multiplication of the force and the distance. You just need to take both of them and multiply them. All right. And then the second thing we agreed on, that if an object doesn't move, which means your distance is zero, there is no work, because in order for work to exist, the object has to move. And finally, the last point, which we said is going to be very, very, very important, the work done on an object is the same as the energy transferred to it. Okay? Thank you guys for listening, and see you in the next video. Goodbye.